Hello, and on behalf of the Advanced Renal Education Program and the Nephrology Campus, welcome to the fourth in a series of webinars entitled Flummoxed by Flux, the Indeterminate Principles of Hemodialysis. My name is Peter Stemmekel. I serve as a professor and senior lecturer at the Department of Renal Medicine, Karolinska University Hospital at the Karolinska Institutet in Stockholm, and this is in Sweden. And I will be your moderator for this session. First, I want to say a big thank you to all the healthcare workers as you continue to provide world-class care to our patients. And we have a large number of attendees today, and all lines have been muted as a courtesy. We do, however, want you to engage with us during the program. In the user panel, please feel free to submit your comments and questions at any time during the program. We have also included handouts of both the presentation and literature article, which will be discussed today. And if you have any additional questions after the webinar, please send an email to the respective regions seen on this slide. And we have a comprehensive webinar schedule, as you see here. Over the course of 8 webinars, we will discuss articles from the supplement recently published in Clinical Kidney Journal entitled The Duality of Dialysis Membranes, Their Attributes and Ramifications. And with these webinars, we aim to help facilitate a better understanding of the functioning principles of hemodialysis with a focus on the critical role of dialysis membranes. Be sure to register to attend when you receive the announcement via email, and we will share upcoming dates later in the program. And this educational program has been developed by Medical Information and Education Office at the Fresenius Medical Care. It is intended to provide pertinent data to assist healthcare professionals in forming their own conclusions and making decisions. It is not intended to replace the judgment or experience of the attending physician or other medical professionals. The treatment prescription is the sole responsibility of the attending physician. And today I am happy to introduce you to Professor Madhukar Misra. Professor Misra is currently Dr. Twardowski Distinguished Professor of Nephrology at the University of Missouri in USA. Dr. Misra is also the Program Director for the Nephrology and Fellowship Program, Director for Acute Inpatient Dialysis, Chronic Outpatient Dialysis and Medicine Specialty Clinics at the University of Missouri Healthcare. After finishing his training in internal medicine in India, he moved to the UK to specialize in nephrology, first at Leicester General Hospital and later at the Hammersmith Hospital's NHS Trust at the University of London. Dr. Misra is also currently the Deputy Editor of Hemodialysis International and Associate Editor of Advances in Peritoneal Dialysis. His research interests include preservation of residual renal function on dialysis and alternative hemodialysis schedules. Dr. Misra has published more than 100 research papers, edited 2 books on dialysis, and also contributed multiple book chapters in prestigious textbooks in the field of dialysis. And we are really thrilled to have Dr. Misra here today to present to us. And with this, I would like to give the floor to Professor Madhukar Misra. Please.
Thank you, Dr. Stenwinkel, for such a kind introduction. As you just heard, my name is Madhukar Misra, and I'm delighted here to be presenting this topic, Flummoxed by Flux, on behalf of all the authors of a recent publication we published in Clinical Kidney Journal. It is a privilege and true honor to be presenting this talk. I have no disclosures to disclose. And let's jump right in. In hemodialysis, when we're trying to eliminate so-called uremic retention solutes or uremic toxins that are retained in uremia. We achieve that by a process of intercompartmental transport, which happens across a perm-selective barrier, in this case the membrane, from the blood side to the dialysate site. All biological and extracorporeal processes involve certain driving forces, and these driving forces essentially facilitate the transfer of molecules across the membrane. Now, the term flux essentially denotes the magnitude of the transport from one compartment to the other, referring to the permeability of the membrane. In all industrial or medical membrane-based separation processes, we need to understand that flux is a finite parameter, and it is used to quantify transport phenomenon, in this case, the volume of fluid transferred per unit area of membrane surface per unit time, with the units of liters per meter square per hour. Now, flux is influenced by the driving force or forces present, and of course the physicochemical nature of the semi-permeable membrane relative to those of the solids to be removed. When the driving force is the transmembrane pressure, flux is often expressed as ultrafiltration coefficient, or KUF, with the units of ml per minute per millimeter of mercury of transmembrane pressure, and then it denotes the hydraulic permeability of the membrane in question. The problem with the use of term flux in hemodialysis can be looked at in many ways. First of all, it suffers from rather lack of precision when we talk about flux in hemodialysis. It is also qualified by certain prefixes such as low flux, mid flux, high flux, superflux, or ultra high flux, without any scientific basis or any scientific reasoning. Furthermore, it is often used interchangeably with other measures of separation in hemodialysis, like clearance, for example. It is also used or referred to as sometimes sieving characteristic of the membrane itself. The sieving coefficient, as we shall see later in the talk, which is a dimension-less ratio, is also often used to categorize flux of hemodialysis membranes, either on its own or in conjunction with the ultrafiltration coefficient. So the lack of distinction between a measure of fluid transport on one hand and an index of solutes' ability to travel across the membrane on the other creates confusion when interpreting flux, and leads to ambiguity and confounds the interpretation of data. Very commonly, flux is often used or interpreted as a reflection of pore size, implying that bigger pores imply higher flux. One needs to understand that we can have, and it is possible to have, two membranes with similar hydraulic permeability or water flux, but may have different clearances of solutes, for example, beta-2 microglobulin, due to the differences in pore size. So let's look at the mechanics of membrane separating process in hemodialysis. The membrane separation process, as we all know, is a process when one component on one side of the membrane is transported more readily than the other components across the membrane. Now, the basic concept for this separation process is the driving force that determines the transport between compartments and across the membrane. This driving force, or the difference between the driving force between the two compartments, shown here is delta x, or the numerator of the equation, delta x over L. So what is this delta X? Essentially, it is the difference of that force, which is the driving force, in that membrane separation process. And this force could be difference in pressure across the membrane, difference in temperature across the membrane, or electrical energy, or in the case of dialysis, when we are talking about a diffusion-dependent process, it is the concentration gradient which is different between the two sides, the blood and the dialysate side. And in diffusion, that is the major determinant of the driving force. What about L, the denominator in the equation? The L denotes the membrane wall thickness, and that, of course, has a bearing on the overall driving force when we are talking about membrane separation processes. This basic concept essentially was behind the development of the middle molecule hypothesis. Because if one thinks about thicker membranes that were available at the time of this hypothesis, it was felt that thicker membranes, because of the nature of them being thick, they limited the removal of middle molecules and resulted in a low driving force because the denominator was higher, the L being higher in the case of thicker membranes. And so that implied that only small water-soluble compounds could be dialyzed, and so-called middle molecules would not be eliminated to an appreciable extent, thereby resulting in all the bad sequelae that we used to see in our patients. Let's pause for a moment and talk about what determines the efficiency of hemodialysis besides membrane wall thickness. Well, we have talked about the driving force, the concentration gradient in diffusive-based removal, or transmembrane pressure, which is the driving force behind the amount of fluid removed across the membrane. Then, of course, comes the membrane morphology, the physico-chemical characteristics of the membrane itself, and then finally the operating conditions during a procedure of hemodialysis. Let's break it down a little further. Talking about membrane itself, the size-selective nature of the membrane is dependent on the solute size, because if you think about it, the solutes that we are trying to remove vary in their sizes. And this particular nature of variance in the size of the solutes essentially imparts to the membrane its size-selective nature. Once the solute is able to come across the membrane from the blood to the dialysate side, the efficiency of the entire therapy then is determined by flux, in other words, the bulk motion of fluid. Now, flux has its own determinants, including properties of membrane, and of course, as I said, the operating conditions of dialysis. And here are some of the determinants or variables that impact the permeation rate of flux. We've already talked about the driving force, in this case being the transmembrane pressure. But if you look at the denominator, there are other determinants that have an impact on the permeation rate or flux, including the viscosity of the blood, and of course, the resistance as the solutes or the fluid travel from the blood compartment to the dialysate compartment. This overall resistance is determined or denoted as RT, and this overall resistance is composed of three resistances. The resistance on the blood side, denoted as RB, the membrane resistance, denoted as RM, and the dialysate compartment side resistance, which is denoted as RD. Let's focus a little bit on the membrane resistance. As you can see on your left, this is a membrane with the wall thickness shown here. The arrow shows the thickness of the hollow fiber, and obviously the thicker the membrane, of course, you have more difficulty for solids in terms of resistance to transfer across the membrane. So what are the key determinants of flux insofar as the membrane structure is concerned? That brings us to two major determinants as far as membrane components are concerned. One is porosity, and the second is type of channels. So porosity, or number of open spaces, is essentially the number of open spaces relative to the polymer in between these holes that are present for solid transport. And by type of channels, we imply the nature of channels or pores across the thickness of these membranes. So on your left side is a typical cuprofan membrane used earlier on, which is a cellulosic membrane. And as you can see, the dark area shows the luminal side or the inner side of the membrane. The outer side is shown on the lower side of the left panel, panel B. These membranes are symmetric in nature and have low porosity, and because of their thickness, they impart increasing resistance to the movement of solids, especially large molecules. To your right is a modern synthetic membrane, which is asymmetric in nature and has increasing porosity. So when you look on the right panel showing you the synthetic membrane that I just referred to, it has an inner side which comes in contact with blood. And then, of course, as you travel from inside to outside, you see increasing porosity. This porous nature of the membrane, as it goes on from luminal side to the abluminal side, imparts the asymmetric nature to the synthetic membrane. Now, the inner side, the innermost layer that comes in contact with blood, imparts the highest resistance to the movement of solids. And as we move from the inner side to the outer side of the wall, we encounter increasing porosity, which essentially serves a scaffolding function, support function, but also because of pores, it offers increasing ability for solids to move across from inside to outside and decreasing resistance. So the pore density in the innermost separating layer is determinant of the primary resistance of the solid movement. What about the resistance that is offered by the blood compartment? Now, as soon as we begin the flow of blood across along the length of the hollow fiber, within milliseconds, a couple of phenomena happen. One of them is the phenomenon of protein absorption. So proteins like albumin and immunoglobulin G and fibrinogen, they come and get deposited on the blood membrane interface. This is followed by the phenomenon of concentration polarization, which essentially implies that certain solutes layer on the top of the protein layer, and together these two layers obviously increase the functional wall thickness and have a role to play in determining the overall solute removal by diffusion as well as convection. So they increase the so-called L in that concept of driving force that we just discussed. Now, ultrafiltration is the major force that drives flux. As we all know, it is a pressure-driven mechanism, in this case, the transmembrane pressure. It is important to note the one major difference between flux with units of liters per meter square per hour and KUF, or volumetric filtration rate, with the units of mils per hour per millimeter of mercury. So KUF is not, as you will notice, KUF is not normalized to surface area, and thus it is a property of the dialyzer, not of the membrane itself. This is a very important distinction. So a dialyzer with membrane, which has got relatively small pores, can have a high KUF because of high surface area. This is a concept that is often not understood completely. Let's now examine the equation that talks about flux or hydraulic permeability. This famous equation, as was expressed by the Hagen-Poiseuille relationship, is showing you the variables that determine the overall hydraulic permeability. We've already talked about L, which was the thickness of the membrane. We have talked about the driving force, in this case, the transmembrane pressure. But look at the other variable that is impacting hydraulic permeability, the fourth power of the radius of the hollow fiber. That has a direct impact on hydraulic permeability. So it is obvious from this relationship that the largest impact on flux is from the pore size, and very small changes in pore size can lead to significant effects on hydraulic permeability. With that background of flux and the variables that determine it, let's now shift gears a bit and look at the perspective of the regulatory bodies and the guidelines that talk about flux and guide us into selecting a particular type of membrane or particular type of therapy. So in 1998, the first attempt was made by United States Food and Drug Administration. In fact, one of its branches called CDRH, the Center for Devices and Radiological Health, that attempted to define the in vitro KUF for a conventional hemodialyzer. Conventional meaning that ultrafiltration controller will not be required. And they defined that KUF as less than or equal to 10 mils per hour per millimeter of mercury. In 2018, the in vitro KUF for a high permeability hemodialyzer was defined as greater than 12 mils per hour per millimeter of mercury, implying that in this high permeability hemodialyzer, an ultrafiltration controller will be required. Subsequently, in 2020, the in vitro KUF for high permeability dialyzers was lowered even further to being more than 8 mils per hour per millimeters of mercury, even lower than the previous guideline. What about the European regulatory bodies? The European Renal Association and the EBPG guidelines of 2007, specifically Guideline 2.1, recommended the use of high flux hemodialysis versus, of course, low flux hemodialysis to delay long-term complications of hemodialysis, and recommended that use of higher flux would lead to beneficial clinical consequences and avoid long-term complications. Use of therapies like hemodiafiltration or online hemodiafiltration was recommended, essentially to exploit the high permeability of high flux membranes. It is worth noting that no mention was made of any criteria for defining flux. In fact, in 2010, Guideline 2.1 stated, after revision, that use of high flux membranes should be considered for all patients, high risk, meaning serum albumin less than 40 grams per liter, as well as low risk ones. The underlying point is that two major trials, the HEMO trial and the MPO trial, used flux as their major core investigative parameter and did not define, or in fact used different definitions of flux, and yet the guidelines incorporated the recommendations from these two trials for guiding therapies as we know them today. What about KDOQI guidelines from the US? after the publication of the EGE trial, what you see here is that guideline 5, referring to the hemodialysis membranes, essentially recommends use of high flux membranes. So low flux definitions and high flux definitions according to HEMO, MPO, and EGE trials are shown on the slide, and of course the guidelines that were incorporated by the societies also shown. So despite 3 large randomized controls trials designed specifically to address this issue of flux, showing no differences in primary outcomes between flux categories as defined in those trials, we get to see recommendations for using high flux without clear definitions, fully realizing also the fact that the goalposts for defining flux were so different in all of these 3 major randomized controlled trials. What about the position of some other societies? The United Kingdom Renal Association Clinical Practice Guideline on Hemodialysis recommends the use of high flux dialyzers in patients with minimal residual function. And again, no specific boundaries of flux are defined. The Kidney Health Australia or CARI guidelines also recommend the use of high flux dialyzers, but do not provide specifications to distinguish between low and high flux. Having looked at the regulatory bodies and the guidelines from societies, let's again shift gears and look at what does scientific literature say about this issue, how to distinguish low from high flux. So Akizawa made the first attempt in 1995 to classify membranes based on their performance, and classified high flux membranes as those having a KUF more than 10 mils per minute per millimeters of mercury, and then went on to define high permeability membranes as those with KUF greater than 10 plus a high Sevin coefficient for unspecified low molecular weight fractions shown here. Dr. Golper, in an alternative classification, classified low flux as being less than 15 mils per minute per millimeters of mercury of KUF, and high flux as being greater than 15 KUF. To your right is shown the table of some selected scientific literature that essentially highlights this problem of ambiguity and arbitrariness. So when you look at the classification of flux of dialyzers in this table in different studies reported in the literature, you can see the variable definitions used in defining flux, and essentially indicates a lack of consensus within the scientific community and the arbitrary nature in the way flux is defined. So both HEMO and MPO studies, if we look at them carefully, were inconclusive in terms of distinguishing primary outcomes based on flux. Of course, post hoc analysis of these studies identified clinical distinction in terms of the benefits of increased flux in some subpopulations, and that led to changes in guidelines. We must not forget the contentious nature of and the different, of course, flux boundaries which are in these trials, which are regularly cited in the literature. Moreover, manufacturers routinely position their products in a certain flux category and use that definition to define or recommend therapies or categories of therapies based on those definitions of flux primarily in reference to KUF of those products. One must remember that KUF and flux, even though they are used such, are not interchangeable entities as we just saw. Now, let's look a little more deeply from the perspective of the industry. And this is a rather busy slide, and I apologize for that, but it is important that we look at it for a variety of reasons. So it shows you the KUF designations and dialyzer types of various manufacturers. If you look at the leftmost column from top to bottom, what you will see is the name of companies and of course the designation of KUF by these companies, which is used as a classifier of different dialyzers these manufacturers use. So if you choose any particular row from top to bottom, move from left to right, you can see that every manufacturer chooses to define their product based on KUF-based classification of flux, traveling from left to right. The first manufacturer, for example, defines 4 types of dialyzers with KUF in ranges of 53, 59, 67, and 75 while traveling from left to right. What does this mean? Essentially, this whole slide tells us that industry sets its own standards for classification of flux, using arbitrary ranges of flux, and then, as you notice, in the leftmost column, travel from top to bottom, using adjectives like low flux, middle flux, high flux, super high flux, and so on. So low flux for a particular manufacturer may be high flux for the other. And then, of course, when you think about FDA definitions defining high flux as being greater than 8 or even 12, then you obviously realize that most of these membranes fall into high flux category. Even if you choose a European definition of more than 20, it is very understandable that most of these membranes again fall into high flux category. And one must not forget that there is the surface area component also here on these slides. So it creates even more confusion when one is using KUF to define flux, and then of course not realizing the fact that the increase in flux is associated with increase in surface area, creating further confusion. What about KUF itself? Well, the whole concept of KUF was introduced earlier on with earlier membranes which were not as refined in technology as the modern day membranes, and required an understanding between the relationship of transmembrane pressure and ultrafiltration rate in achieving a certain degree of KUF. So the previous versions of dialysis machines, as some of us may remember, required us to be aware of this linear relationship till a certain level, beyond which it plateaued out, of the relationship between ultrafiltration rate and transmembrane pressure. Now, in automated volume-controlled ultrafiltration machines, the modern day machines, which achieve a steady ultrafiltration rate throughout the session, this understanding of UFR, or ultrafiltration rate, and transmembrane pressure as a determinant of KUF is perhaps no longer required, because if we want to remove a certain volume of fluid, all we need to know is the session length of that particular hemodialysis session and the amount of weight that we need to lose in a particular patient, and the machine does the rest. So the KUF that determines the transport process of flux and is a cornerstone concept is, for lack of a better word, is more of a scientific concept for classification of therapies and has assumed more commercial value than any practical value or clinically relevant value. Now, having looked at flux as one of the major factors when we are talking about the quantification of fluid transport, let's look at some other membrane features that have a very important role to play in determining the selectivity of the membrane. And one of them is the sieving function of the membrane, because sieving function of the membrane in a membrane-based separation process essentially decides which solutes get to pass through the membrane and which solutes do not get to pass through the membrane. And essentially, the sieving property of the membrane is dependent on the pore size. It's pore size dependent. And of course, the geometry and distribution of pores at the innermost separating region of the membranes are very important in relation to the size and conformation of the solutes that we are trying to remove by making them pass from the blood side to the dialysate side. So light flux, the selective nature of the membrane, which is a membrane performance measure, is expressed by two different but closely related concepts of solute sieving and retention or rejection. So one of the ratios that is often used when we're talking about the nature of sieving is called the sieving coefficient. And the sieving coefficient is a dimensionless ratio, as we earlier saw, that tells us the ratio of the concentration of a given solute in the ultrafiltrate, shown here, and the denominator being the concentration of that solute in plasma water. Now, this is essentially the sieving profile of a high flux membrane, with the sieving coefficient shown on the vertical axis and the molecular weight of different solutes shown on the horizontal axis, from 100 on the left to 100,000 to the right. So when you look at it carefully, a sieving coefficient of 1 on the top essentially means that solute passes freely through the membrane. In other words, there's 0% retention of solute in the blood. If you go to a sieving coefficient of 0, it essentially means that almost all of the solute is rejected, meaning none of the solute can pass through the membrane. 100% is retained or rejected. And in between these two limits of 10,000 and maybe 30 to 40,000, this sigmoidal portion of the curve essentially denotes the nature of the molecules that will be able to pass across this particular high flux membrane. So the sigmoidal portion of the curve essentially is showing us that smaller molecules will pass through with relative ease as compared to relatively larger molecules. Now again, we must remember that the sieving component or the sieving coefficient profile of any given membrane is not derived from in vivo measurements. It's an in vitro measurement using lab parameters for polydispersed dextrans of different molecular weights as surrogates of uremic toxins. And so there are differences between in vitro and in vivo sieving functions, which are determined by several of the parameters that we have already talked about, including concentration, polarization, the plasma protein absorption, the physical chemical characteristics of the membrane itself, the operating conditions of dialysis like the blood flow rate and the transmembrane pressure and so on. So these are dynamic phenomena that determine what is the in vivo sieving function as compared to the in vitro that we talk about. Now, these are the innermost layer of these EM scanning photographs of the innermost layer of the membranes, 7 membranes for that matter, that show you the diversity of morphology of the innermost surface which comes in contact with the blood. So what is trying to highlight here is that these membranes, 7 membranes shown here, may have clear open pores of various sizes, or may have fissure-like tears shown here, or may have diffuse gaps without any discernible pore-like structures. And so what is the relevance of these diversity that is shown by these 7 membranes insofar as surface morphology is concerned? Well, the point to highlight is this, that there may be several pores which may be much larger than what is specified in the specification characteristics of that particular membrane, simply because the pore size distribution is so variable and so broad. And so there may be fissures or open spaces that may be of several sizes more than the size of the albumin molecule, for example, with a molecular weight of 68.8 daltons, 66.8 kilodaltons. And so it may allow such big molecules to pass, even though when you read the specification sheet, it may not say so. And remarkably, all manufacturers essentially claim that the properties of these membranes are essentially comparable when it comes to retaining larger molecules, which is very interesting, because as we see that there's so much diversity that these properties of retaining larger molecules can certainly not be comparable across these membranes. Well, the HEMO and MPO trials led to the extrapolation of the definition of flux of membranes to include sieving coefficients and beta-2 clearance, thereby creating a multi-parameter categorization of flux of membranes. When one uses sieving coefficient to define low versus high flux, it distorts the membrane classification even further. More recently, it has been suggested that we use beta-2 clearance to distinguish dialyzers of different flux. So low flux having a beta-2 clearance of less than 10, mid flux between 10 to 20, and high flux being defined as a beta-2 clearance of more than 20 mils per minute, also sometimes with a beta-2 sieving coefficient of greater than 0.6. And the story doesn't stop here. So here is a slide that is essentially being included to highlight one important point, and that is that the clearance of beta-2 may also be used for reimbursement purposes. At least in the Japanese reimbursement model, as we see here, there are 5 categories of reimbursement class. Less than 2 beta-2 clearance being reimbursement class 1, and then as you can see, if you travel from top to bottom, the highest category is more than 70 ml per minute beta-2 clearance. And as we travel from 1 to 5, the reimbursement level goes up, even though it is not linked to the flux itself, meaning the reimbursement is not linked to membrane designation of flux, but it's linked to the beta-2 clearance. Nevertheless, it is interesting to note the adjectives used for classifying flux on the rightmost column, from low to classic high to super high flux, with no defining category between high flux to super high flux. So one of the problems with this is that when you rely on a single uremic toxin whose kinetics of removal are not representative of other uremic retention solutes, then it's a problem. And the association of beta-2 clearance with flux confuses this issue of flux overall even further. When we talked about sieving as one of the membrane properties, we talked about 2 relatively related concepts. One was sieving, the other is the membrane cutoff or rejection or retention. So the concept of membrane cutoff is another alternative to indicate the specificity of a membrane. The sieving coefficient we've just discussed. The sieving coefficient is inversely related to the rejection coefficient. Or in other words, sieving coefficient is the reciprocal, as is shown here, of the rejection coefficient. So if you look at the sieving coefficient profile on your right panel on the top, one can see that a sieving coefficient of 0.1 essentially means that for this particular molecule, let's say weighing 30,000 Daltons, only 10% of that molecule will filter through. So if you look at the bottom panel, this essentially translates to that this particular molecule with a molecular weight of 30,000, 90% of this molecule will be retained. Regardless of sieving or rejection, the decisive determinant of the transfer of the molecule is the size distribution of pores. And then again, because it's a dynamic phenomenon, it is not only the size distribution of pores, but also the ongoing phenomenon of protein absorption, concentration polarization, and the driving force that is the transmembrane pressure. All of these basically combine together to determine what will and what will not pass through the membrane. Now, there's another thing that is extremely important to understand, because we tend to think the molecular weight cutoff that is often specified in the specification information that is available to us when we are choosing a dialyzer. Let's say we see a membrane cutoff of 30,000 for a particular solid. We look at it in absolute terms, and using this panel as an example, we might tend to think that a molecular weight cutoff of 30,000 implies that molecules with 30,000 with a molecular weight of 30,000 or above will not be able to pass through the membrane, whereas in fact it essentially means that 10% of such molecules will still be able to pass through the membrane, 90% will be retained. So contrary to the claims made by manufacturers, it is obvious that pore size distribution is not narrow across the membrane and is widely distributed and is variable. And so one must try to understand this concept and keep that in mind when selecting membranes to choose a dialyzer or for a particular therapy. So in conclusion, flux or hydraulic permeability of the membrane is often quantified by KUF, and KUF is proportional to the applied transmembrane pressure, as we have just seen, and its value depends on various other parameters that we have just discussed. It is often erroneously used as a measure to indicate the ability of dialyzer to remove middle or high molecular weight substances, given the discussion we just had. And then, of course, we use these definitions to prescribe hemodialysis. And of course, in some instances, as we have seen, the reimbursement is defined or decided based on clearances. We design trials based on definitions of flux, as we have seen in different trials. And then we use adjectives, using low, mid, high, or superflux membranes defined according to shifting criteria, and then use them for defining or choosing therapies, implying ascending effectiveness and superiority of one over the other therapy. Obviously, this is a flawed concept. We have seen the problems when we define flux with clearance in mils per minute, and the problems associated with defining flux with sieving coefficient dimensionless ratio with no units. and that too for a single protein. There are problems with loss of albumin, which is measured as units of grams lost per treatment session when we associate flux with loss of albumin together with KUF, the units of which are different than that of flux. And again, highlighting the fact that when we use these industry-defined adjectives of low to high flux, it creates further confusion, remembering all the time that the pore size distribution is relatively broad. It's not narrow. And the innermost nature of the membranes across the industry is not comparable insofar as loss of certain high molecular weight solids is concerned. It is not only broad, but it's also variable, as we just saw. What about KUF and flux? Even for KUF, there's little unanimity in terms of what defines its boundaries and how to classify KUF in relation to flux. And that makes it difficult to discern between the different categories of flux as defined by industry in terms of terminology of high flux to super high flux. And so we have the story of shifting goalposts for flux which keep changing. So previously defined dialyzers which were high flux may be now determined as being low flux. And then, of course, we cannot ignore the lack of guidance from regulatory bodies in official guidelines when it comes to defining flux. Usually, these regulatory bodies, when they define their guidelines, have fastidious deliberations and are very, very careful in using terminology, but not so in case of flux. And such imprecise definitions of flux basically have impact on patient outcomes because of their use in clinical trials. And then, of course, patients' perceptions obviously get misplaced. And lastly, we've seen the problems when we try to associate flux with reimbursement, the definition used in this particular case being the clearance of beta-2 microglobulin. Now, when we use membrane classification based on selectivity criteria like Civic coefficient is even more problematic because when you use a single value, a Civic coefficient-based categorization of flux could literally have dozens of Civic coefficient values depending on the molecule in question. That is one problem. And the other problem is that the Civic coefficient profiles, as we've just seen, are subject to dynamic phenomena like concentration, polarization, protein absorption, etc. And so that creates another confusion when we are talking about classifying flux based on membrane selectivity criteria. So to conclude, flux in hemodialysis deserves better clarification by the regulatory authorities and scientists alike, and that will go a long way in preventing its misappropriation. Thank you very much.
So thank you so much, Dr. Misra, for this very nice talk about flux. And we have some time now for questions. So if you have questions, please post them in the chat. Meanwhile, I'll have a simple question for you, Dr. Misra. Is KUF a good measure of flux?
So yes, given the complexity of the definition of flux, as we've seen that KUF, if you think about it, is dependent on the transmembrane pressure, which is the major determinant of the ultrafiltration-based removal. So transmembrane pressure is one of the major driving forces, the delta P in that equation. And so when we are talking about flux being defined by the driving force, in this case, the transmembrane pressure, KUF is relatively close to defining hydraulic permeability. The problem is that, number one, we have to remember that KUF is the property of a dialyzer, not of the membrane itself, because it is not normalized to the surface area. So we have to remember that. And it is possible to have membrane or dialyzer with small pores, but a high flux simply because of the high surface area. And so as long as we are cognizant of the concept of how flux and KUF are related, I believe that it is perhaps at this time one reasonable way to look at flux.
We have an interesting comment and questions here on the chat. Many years ago, 1979, Hjelte Hotzke Snell used coprofan and collected spent dialysate and found significant amino acids and small peptides in dialysate. And are there any such out there on the more modern current membranes?
Yeah, excellent question. Because I believe we have seen over the years this concept of high cutoff membranes. And I refer to the question in a little more detail with this background. And so high cutoff membranes or protein leaking membranes were essentially designed with this whole idea that bigger pore size essentially will make us lose so-called protein-bound toxins, which are quote unquote detrimental to our patient's health. And then we have seen, of course, they fell by the wayside. This whole concept fell by the wayside. Now, there was a very interesting study early on, I believe it was in 2006 when it was published, when a group of investigators looked at what is actually lost when we use high flux versus low flux hemodialysis from uremic plasma. And if I remember it correctly, about 1,400 polypeptides were collected in the dialysate using a high flux membrane. When a low flux membrane was examined, about 1,000 or so polypeptides were collected on the dialysate side. And almost all of these polypeptides had a molecular weight less than 6,000 Daltons. With that background, let's now look at what toxins are we trying to remove. So the UTOX classifies uremic toxins as the ones that have the most amount of evidence insofar as their harmful or detrimental nature is concerned. So when you look at the UTOX definition of so-called harmful toxins, which may be protein-bound, only 100 of such solutes exist. So when we are talking about removing toxins, we remove thousands and thousands more than what we actually know are known to be harmful. And so, in other words, we remove a lot more than what we should be trying to remove by designing membranes which are modern insofar as the pore size is concerned. And in terms of toxicity, as far as we know, for now, only 100 or so uremic toxins are known to be biologically harmful. And as we have seen, the study showed we removed almost 1,400 of polypeptides in that molecular weight range. So it is good to think in terms of removing toxins, but it is an ongoing exercise to, when we talk about this whole concept of more higher molecular weight toxin removal we do, the better it is for the patients.
Thank you so much. Again, I really like to thank you for this erudite lecture you presented here. And also I like to thank all you out in the audience for joining us today. Now there will be summer vacation here, but please be sure to register for our upcoming webinars. And the first one after summer vacation will be on September 13th. And then Professor Alberto Ortiz will talk about hemoincompatibility in hemodialysis, alleviating inflammation and anticoagulation. I'm sure this will be a very interesting webinar. And October 4, we have Professor Bernard Cano that will talk about multi-targeted interventions to reduce dialysis-induced systemic stress. So have a good summer vacation. I hope to see you again in September. And for those of you that are in Europe, I will say good evening. And for those in US, have a good day. Thank you so much.